course. Today we'll look into robot electrolyzed particle filters again for building maps, but this time we don't look into feature maps but into grid maps, so these kind of dense grid maps that we discussed last time as well. But before I start, I want to have just a kind of 5 minutes very shallow introduction to scan matching, because it's just one technique we are going to use in the next approach, but I won't go into technical details, just that you understand what this technique is doing, what it is used for, what are advantages and disadvantages. So last week we talked about grid maps and how to build grid maps given you know the poses of the robot. And the straightforward approach would be, if you have a system you want to build a grid map, just take your raw odometry information. So take odometry, assume odometry is perfect, and then build a map based on the odometry information. The problem that you have if you do that and you have a robot which doesn't have a very good odometry, you will get a result which looks like this. So the red line here is the trajectory of the robot, and while it moves through the environment, it builds a map. It's actually the Intel data set for those of you who have seen that already. And so you can see here where the robot moves through the environment, that you can locally actually guess structure if you just look to the local scans. But this, having integrated this into a map representation, is clearly nothing you could use for navigation. So the idea of just using pure odometry or raw odometry and assume it is perfect doesn't work. So the reason for this is that the motions are noisy. So the motion commands that the robot executes are affected by noise. The noise can depend on the floor, on the type of ground, on the wheel. So we discussed all these things in the motion model. But just this would be a real world illustration that assuming known poses from odometry typically fails. You can typically do somewhat better than what's shown here by kind of calibrating your odometry and do certain steps. But if you take the raw odometry as the robot is often delivered, that's what the result looks like. However, if you look to the sensors we have attached to those robots, especially if you work with laser rangefinders, which are typically used to build those grid maps or proximity sensors in general, you actually see that those laser rangefinders are typically pretty accurate. So if you leave them in the environment, you scan the same part of the environment, they will report the same measurements over and over again, and they are pretty accurate. So the question is, can we actually exploit that, these high accurate sensors, with all motions not very precise? And it turns out that we can actually do that, and scan matching can be seen as probably one of the simplest approaches to do that. And the key idea is to take the current scan we have and look into the motion that the system predicted, so where we move from the last point in time to the current point in time, and then compare the current observation and the previous observation. And then try to align those observations. This is why it's called, every observation is a scan, and I match both of them onto each other, and therefore it's called scan matching. And this works because in a lot of cases, as I said, the scan information, so the observation, is much more accurate than the motion estimate taken from odometry. And so this can be exploited, and one technique for this is called scan matching. You can either match two scans, you can match a scan against a map, you can match two maps, you can match features, you can match grid structure. So there's a kind of, let's say, a big zoo of different scan matching approaches out there. And but I just want to give you kind of the very rough idea of what's going on. And what scan matchers typically aim at doing in every time step is actually maximizing this expression. This expression is not like magic. It consists of two terms. The first one you see here is the term that should be familiar to you, and this is the observation likelihood. Laser pointer doesn't work anymore. So the first term over here is the observation likelihood. The likelihood of the observation given the pose, xt, and the map. And here the map has a time index. It means it's the map we estimated so far. That's what it should express. And times, this is the motion model. So where's the robot at the current point in time, where it was, we know where it was before, and the odometry information. So what is this approach doing? It tries to, given that we know, on the assumption we know where the robot was before, this is x t-1 start, we just check where did the robot go. There are different ways for doing this. Let's say you take first odometry, then you take the current scan which was recorded at that location and the scan which was recorded previously, you try to align those two. This kind of can shift the pose a little bit, that it perfectly aligns with the observation. And what this equation does, it's kind of the scoring function for this alignment, if you want to see that, consists of a product of two terms. The first one is the observation likelihood, that means we're just matching the observation. And the second term of this product is the odometry information, so how likely is it that the robot actually drove there. It's just a product of these two terms. But the thing is, it's actually dominated, the peak is typically dominated by the observations. And this just gives you kind of the rough area we need to search into, because typically say the odometry error is bounded, so the robot is not teleported away somewhere else for one time step to the other. So you kind of know the local area you're searching in, and within that local area, the product is typically dominated by this term. And what the system does, it does a scan alignment and fixes the pose that the most likely pose of the robot was the pose we are currently in. And then it says, okay, now I suppose is supposed to be given. So everything which is starred is kind of assumed to be known, mapping with known poses. And then you continue to progress. So it's just kind of the correction of the current pose given what I've built so far by aligning the scans with the map I've built so far over the previous scans. That's called scan matching. So it cannot account for things like loop closure, all these kind of, let's say, more sophisticated things that we did in SLAG. It's just a very, very basic technique. You can see that there's a kind of an easy way for correcting the odometry if you have an accurate sensor. And so as I said, there's a whole zoo of different scan matching approaches out there. The most popular one is ICP, iterative closest point, and the key idea is you have match two scans, and often two scans, and you just say a point in one scan, what's the closest corresponding point in the other scan, and then you try to minimize an error function so that those two scans overlap at most, so that the distance between the corresponding points is minimized. You could do this from a scan to a map. You can also use a very similar approach to map a scan to a map, or a map to a map, or point clouds to point clouds, or features to other features. So there's a whole variety of techniques to do this. You often find techniques for outlier rejection, that you can say few points here are outliers, they're not considered in the matching, the really bad matching ones. And correlative scan matching is also one approach which maps the scan to a map, which is pretty common. But I don't want to go into the details, just to give you an idea what scan matching is, because we will use it later on in the approach. So this is what scan matching can look like. So these are kind of two maps, or two 3D scans taken with the robot. The blue one and the red one. So the blue one is the previous one, the previously recorded scan, and the robot drives, let's say, 3 meters forward, takes another 3D scan. And you see where the offset started. This was kind of the error that odometry made. You see in a second. Yes, no. And then by just trying to align those maps based on the observations, you can see it's the iterative process which aligns those maps unless they are nearly perfectly in line. Here you can even see the lamp, which has been previously 2 lamps, and by optimizing the transformation between those two locations where the scans have been recorded, you actually improve the odometry. That's kind of standard technique which is out there, which is popularly used, say, at the beginning of the 90s. I think ICP was invented or proposed to these. There's the reference from robotics field. So if we take the data set we had before, the internal research map, this one over here, and run a scan matcher, that's the result that we get. So you can see the result is dramatically better. And what this approach does, it just takes the current scan and matches it against the previous N scans. So use the previous N scans, kind of a window, a sliding window approach. It just matches the current scan against the previous whatever N scans, 20 scans, and then you get a result like this. You still see here when the robot revisits part of the environment multiple times, especially here on top, you can see that the map is still imperfect, so it's not perfectly aligned. But this result is dramatically better compared to this one. And you can also see that if you compare, or you can now also create a motion model, which is, for example, done based on the scan information. So the small example over here, you see if raw odometry spreads the robot like this, so you can see the robot moves along this trajectory, and this is kind of a sample-based representation which tells you the uncertainty of the motion. If you would do the same for scan matching, you typically end up with an uncertainty which looks like this. So there's still uncertainty involved, so the uncertainty is not zero, you still make errors, but the errors are much, much smaller compared to the raw odometry. So scan matching is just an incremental technique which just matches the current scans against, as in the previous N scans or very local map that we built, and we just kind of can use this to either optimize our odometry, or what we can do is, let's say, given we have a scan and we say what the most likely, or a small map, and we say what the most likely location where this scan has been recorded in the local area. Okay, let's say start point, and then we kind of do a local optimization, match the scan against the map until we get the perfect or close to perfect alignment. This technique is always kind of often optimization or error minimization or gradient descent based technique, and it always ends up what we call the local minima. So it never said that the result that the scan matcher found is a globally perfect result. Not at all. But in the most cases, it is actually the global one, but definitely not always. The error to the global one is also small. And it's a quite useful tool which is often used to pre-correct information. But it's definitely not perfect. It's quite likely that within a large data set you will make errors with scan matching. Sometimes there's some weird artifacts and you could, let's say, move the scan by 45 degrees and it matches quite perfectly the scene. So you kind of can also have multimodal beliefs, and these are the problems you typically have with scan matching. Nevertheless, it's often used, and we also use it as a small building block in an approach which I'll present in a few minutes. So, kind of just to sum up, scan matching can be used to improve the odometry information, and thus can be used to improve mapping with node pulses dramatically if we have scan matching compared to a situation where we use raw odometry. It typically produces locally consistent estimates. Again, not always, but in most cases. That means if I align a few scans, they look, there's a quite consistent map. However, if I stack a large number of those scans together, it's typically is not globally correct or globally consistent. We have global inaccuracies. That's the reason why we really do SLAM, where we may need to optimize the whole maps, the whole map of the environment and the trajectory of the robot. So what we did. This can be seen as a very crude approximation to SLAM, scan matching. But often it's not sufficient to build maps. So there are just two references I want to show you. The first one is the Besson and McKay. This was the introduction of ICP for aligning two scans. There's a more recent technique by Evan Olsen on real-time correlative scan matching, which is a pretty good scan matcher, which a lot of people use today, which aligns scans to a map. And just if you're more interested in that, then especially the work of Evan Olsen is worth to read. There's just some background information if you want to know more about the scan matching. As I said, it was kind of, well, probably not 5 minutes, but more 10 minutes. Very short introduction to scan matching, but as I said, we just want to use this as a building block later on, that will just want to tell you what scan matching is. Are there any questions about scan matching as presented here? Yes, please.
Can it be used for particle filters where we have different hypotheses for Raman filter?
No, so scan matching in general is completely decoupled from the particle filter. It just means that you take your scan, you align your scans. So most people who use scan matching actually use this kind of as a pre-correction for odometry, and then do something else with their odometry. Let's say feed it into a SLAM algorithm, for example.
And what's the difference in idea of scan matching and the idea we have, for instance, in column filter and EKF, when we take the predicted observation, take the real observation, and then using
Okay, so this is definitely related. The main thing is what scan matching does. You always kind of you just take one step and then you fix the rest. So for the EKF, if you were driving through the environment, you do a prediction step, a correction step, and so on. And whenever you observe something, it also changes the correlations, for example, of all the landmarks we had. Or when we close a loop, we kind of correct the whole map. This doesn't happen at all in scan matching. It just takes, it fixes the past. It just makes the next correction optimize it, says now it's fixed, it cannot be changed anymore. So it's just really incremental, step by step, so to say, without having any possibility to do any corrections in the past. And therefore it's efficient because it doesn't have to care about the past, it typically doesn't store anything about the past, just let's say the last few scans. Therefore it's much more efficient than an extended column filters. Yes, please.
do you put the scan matching between the prediction and the correction step?
No.
After telemetry and apply scan matching and then
So typically, I haven't talked about in any way how we're going to use this, but how it's often used is just scan matching is done as kind of pre-correction step, because then you have smaller uncertainties in your motion in most cases, and then some other SLAM algorithms run on top of that, where it's assumed to be just a better motion model than a pre-correction step. Or sometimes people use it to, given we have the scan here and we have a current scan, where are we relative to the other scans? So we can actually match those two scans and say, I'm currently here, but I actually should be over here. For example, for computing an expected measurement or something like this for these grid cases. It's one way one can use scan matching for. How we're going to use this in this hour, in this course right now, I haven't talked about yet, but I will do that. Any further questions about that?